is on spectroscopic methods. Now, in Unit 4, today being our first meeting, we will look at the first session under Unit 4, which is on infrared spectroscopy. Now, at the end of the session, you are going to learn more about infrared spectroscopy. First of all, we would want to talk about what infrared spectroscopy is and how is it helpful in analyzing organic compounds. Now, infrared spectroscopy is a powerful analytical tool to reveal the functional groups in a molecule. Now, more specifically, it provides information about the nature of the bonds that are in the sample being analyzed. The chemical bonds in compounds actually absorb electromagnetic waves at certain energies, and then it converts them into rotational and vibrational kinetic energy forms. So different bonds absorb the IR radiation at different wavelengths, right? So depending on the kind of the bond, maybe if it's a carbon-carbon double bond, carbon-carbon triple bond, carbon-carbon single bond, all these absorb infrared spectroscopy, or sorry, the infrared wavelength at different frequencies. Now, infrared spectroscopy is mostly used in organic chemistry, but then it's also used in inorganic chemistry as well. Now, the most common type of this IR spectrometer that we have is the double beam dispersive instrument, although the FTIR is also rapidly gaining popularity in IR spectroscopy. FTIR is the Fourier transform infrared spectroscopy. Okay, so in IR, before you run your sample, you have to prepare the sample. Now, depending on the sample that you have, it will inform what kind of sample preparation you should go through. So solids are prepared separately or differently from liquids. Now, there's an instrument or a device or an equipment that is used to prepare the samples, or an instrument to which the sample is applied to be run in IR. Now, I think I've already mentioned this in the previous slide, that the instruments or the equipment we add our sample to, this glass rod, mostly has to be um, made of a kind of material which do not absorb in the IR region. Right? So these are made up of alkali halides or silver halides. So this material is made up of an alkali halide or a silver halide, so that whilst you add your sample to it to run your samples, the samples don't end the equipment itself, this cell itself does not also absorb and add up to the absorption wavelength you are going to read. So for liquids, the most common type of organic samples, one or two drops of samples of the sample is added to this salt plate, and then it is covered and then smeared out, just to make sure that the sample evenly spreads on the surface of the cell. Now, for liquids, there are three different types of preparation, sample preparation. We have the first method, where you dissolve your sample in an amount of dichromethane, and then you add it to the plate, and then just of course, just as you treat the liquids, you put the two cells together, and then you make sure you clean any trace of spillage around the cell. Okay, so the next approach is to make pellets of your sample, your solid sample. So this time around, you crush your solid sample into a powder form, mix it with potassium bromide sample powder, which is made into pellets before the sample is run. Okay, so next is the no mold process. Here, your solid sample is crushed into fine powdered sample, and then it is mixed with a type of mineral, or you known as no. So it forms a kind of suspension which is added to the cell, and then you run your IR with that. Now, there's one thing you need to know about this no mold process. Now the NUO has an absorbance in the IR region, right? So if which I mean of course corresponds to the CH bonds. So if there are alkyl groups in your sample that you are running, then the normal process of solid sample preparation isn't advisable. Okay, there's also the bond vibrations to talk about when we talk about infrared spectroscopy. Now, the energy emitted in the IR region is sufficient to change the vibrational state in the bonds of molecule. So, in order for the molecule to absorb in the IR region to induce bond vibration, there must be a change in its dipole moment as it vibrates. And this change can be either in the size of a dipole um, moment or in the location of the the bond or that functional group you are looking at. So if you consider a typical example in this molecule HF. Now in HF you know that the fluorine is highly electronegative than the hydrogen. So obviously the dipole moment changes as the fluorine moves away and towards the hydrogen bond, leading to the bond stretching, right? Now, if you consider a compound like or a molecule like nitrogen gas and oxygen gas, these do not absorb in the IR region because there's no dipole moment that leads to any stretching, right? So the in nitrogen gas and oxygen gas, in these two molecules, there's no vibrational modes that are no vibrational moments exist in them because of the absence of a dipole moment. Now, in the infrared region, the vibrations are strongest when the dipole moment is large. So, if the change dipole moment is huge, then you can have a strong peak. So, in infrared, you realize that unsymmetrical carbon-carbon single bond stretches are weak. However, the carbon-oxygen stretches are very, very strong in IR because of the difference in the dipole moment. Okay, there's also vibrational modes, and mostly when you talk about vibrational modes, it's what leads to the degree of freedom, right? So for a linear molecule, the degree of freedom which is associated to it, the vibrations is 3n, is given by the equation 3n minus 5. Whereas for a non-linear molecule, the degree of freedom, which is also associated to the vibrational modes, is 3n minus 6. Okay, so the fundamental question that comes with um, IR is assuming you are analyzing a sample or a compound which you do not know its um, structure. How do you tell that now you've been successful in identifying the structure of the compound? Now it's easy when the compound you are trying to analyze is a known compound which has been published in literature. Then after the whole thing, what you do is you compare your spectrum with literature spectrum to see how successful you've been. However, in the case where you do not know the structure of the compound, right, and you want to characterize it using the IR spectroscopy, then it kind of um, makes it difficult, right? So basically, what you need to know is to learn how to interpret the IR spectrum. So step one, you look at the overall spectral band shapes. That's the first thing you have to do. You have to make sure you know the shape of the bands that are being shown in the spectrum. An ultra sharp spectrum indicates an aromatic compound. A broad resonance indicates an inorganic compound. And very broad resonance indicates hydrogen bond groups. So there are quite a number of um, um, things you need to take note. The kind of peak you have in a particular region tells us the kind of functional groups that are present. So any peak around somewhere 1600, 2800 tells us that there's that this kind of functional group there, there's that kind of functional group present. So if you have a peak around 1700, it indicates that there's possibly a CO double bond group, a carbonyl functional group. And if you have a peak at 2050 per centimeter, then it kind of indicates that there's a carbon nitrogen triple bond or thiocyanide group, right? There's also the hydroxyl group. So if and then of course the amine groups, the alkene groups, and all these have certain um, wave number peaks that you always need to look out for. So the moment you learn to identify these peaks at specific wave numbers, it helps you to know the possible functional groups that are present in your organic compound you are analyzing. So a more recent innovation is the computer spectral search program. Now, what happens is one input into the program, the IR peak wave numbers that you get from the spectrum, and the program searches its files and tells the user which compounds are likely matches. So, I mean, it helps us. So, what you have to do is you run your IR spectrum. If it is difficult to interpret it, then you can input these wave numbers into the software, and the software will give you possible match. And sometimes some of these instruments, IR instrument has the program as an inbuilt program where it kind of runs it, and that software picks the wave numbers by itself. The instrument picks the wave number by itself and then gives you possible matches. And there are also other programs. The Aldrich Chemical Company also has other databases where you can also enter your IR wave numbers to give you possible matches, and also the Sattler, yeah, also one of the prominent databases where you can get more IR information on the compound.